Thank you, Ali. Thanks for having me. It's great to be here, and thank you all for being here as well. So today I'll be talking about predicting human visual memory using deep learning. So to motivate like the big picture or the high level of my work, let me show you an image. Or let me not. All right, I think. There we go. Yeah. OK, so as soon as you see this image, using your memory, you can retrieve that, you realize that this seems like a hostile situation. The guy on the right seems to be pretty angry with the guy on the left. The guy on the left doesn't seem to be taking the guy on the right too seriously. And there's a whole host of information that we can tell about people just by looking at a single image. And the question that I want to tackle is, can we build machines to do the same? So essentially, can we build machines capable of predicting human behavior? So in my work, I have looked at this from three different perspectives. Firstly, can we predict memory? Or essentially, can we predict what things people remember? Secondly, can we predict private traits? So can we use images to tell something about someone? For example, can we tell their personality? Can we tell their political inclination? Thirdly, can we predict someone's state of mind just by looking at them? So can we tell if someone is normal, thinking, drugged, drunk, maybe specify which drug, and so on, just by looking at an image of them? Today, most of my talk is going to be focused on memory. So let me begin by talking about that. So memory is at the very core of human intelligence. Without memory, we would not be able to recognize people, places, or things. Without memory, we would not even be able to develop language. So wouldn't it be great if it were possible to predict what kind of things people remember? Let's imagine for a moment that something like this were possible. What could we do with it? So here's a problem which I'm sure many of you have not thought of, but it's one of the most important problems plaguing teenagers today. And this is the problem of selfie selection. Essentially, teenagers are taking selfies all the time and trying to figure out which of them to upload to their social networks, right? So if we were able to predict which of these selfies are going to be memorable, maybe we could make their job significantly easier and save them a whole host of time, which they could spend developing deep learning algorithms or studying other things. Jokes aside, more generally, this problem can be thought of as one of content summarization. So given a set of images, can we find the few images that capture the memorable moments in your album? Sorry, this. Further, given a video, can we find the frame that will allow you to retrieve this video from your memory? Another application is in advertising. So people are trying to develop ads all the time that are memorable. So if we could predict which of the ads are going to be memorable, for example, this one, which is for funeral services, maybe we could add some objectivity in advertising. And this application is one that I'm sorry, I'm going to replace the clicker. It's really. What? Yeah, I actually have one. I can just, it's been really terrible. Oops. Yeah, I think I've got one. All right. Yes, so this is working. Cool. Yeah, so this application is one that I'm personally really excited about. If we could tell which content were memorable, maybe we could make the process of learning significantly easier because students wouldn't have to work as hard to memorize this content. So now, how do we go about quantifying memory? In order for all of us to learn how to do that, I think the best way would be to participate in the experiment itself, which is the visual memory game. So what I'm going to do is I'm going to show you a set of images, one after another. Each image will be shown for a short time, about a second, and your job is going to be to clap your hands when you see an image that you have seen before. All right? It's pretty straightforward, okay? So don't mess this up. So let me see those hands. Do you guys want to test if they're working? Okay, great. Some of them seem to be working. So here goes. Awesome. Excellent. I'm glad that worked out. And everyone was perfect. It's the first time this has happened. People often screw up on some image or the other. But essentially, you guys were clapping. What we did is we designed a task on Amazon Mechanical Turk where people were pressing a key when they saw an image that they had seen before. So essentially what we did is we showed each image to a whole lot of people, and we collected these clicks. And based on this, we defined a metric called memorability, which is essentially the proportion of times a click was correctly, an image was correctly detected when it was shown. So for example, if an image was shown to 100 people and 80 of them correctly detected the repeat, then the memorability of that image was defined as 0.8. Okay, just 80 over 100. The cool thing that we found is that if you repeat the experiment again and again, the memorability scores of images actually remain very consistent. So, yep.
You seem to be suggesting that it's a property of the image, but it also depends on the distractors, right, on the other images.
To some extent. So, so far when we have tested, it is to a large extent the property of the image. So there is some contribution, there's some individual differences across people, but on average, the set of images that people tend to remember or forget are very similar.
If I showed you 10 previous images that were infinitesimally different from the one that you're saying, the memorability would be very different.
Sure. So you can always construct pathological cases where it doesn't work. But given some sort of natural image distribution where people will question what natural even means, but essentially you can imagine downloading a set of images at random from Flickr. You can even say, oh, let me fix the query and say cats, and you download a whole bunch of cat images. Where there's a natural distribution across those images, that is where the effect holds. But instead where you make changes that differ by 1 pixel, everyone is going to mess that up. Yeah.
If I was, say, a botanist, and you were showing interspersed in these pictures a bunch of flowers, I'd probably do a really good job.
Mm-hmm.
So it seems to me that what you're capturing is sort of the lowest common denominator, the interests that a very broad community share.
To some extent. I mean,
it seems to me it's popularity, maybe.
no, it's not. It's what people. I mean, there's some correlation between the two attributes of popularity and memorability, but memorability is what people remember, and it's rather different from popularity. So it's essentially.
I think we remember best what we're interested in, and everyone has different interests.
There might be some individual differences, but on average, okay, let's put it this way. So let's imagine there's a cat person and a dog person, right? So maybe the cat person is great at remembering cats, the dog person is great at remembering dogs. But my hypothesis is that the cat person would remember the extremely memorable dog images, while the dog person would remember the extremely memorable cat images, even if the cat person tends to remember more cat images on average. So if you take an average across the entire population, people would tend to remember, so even after taking an average across this entire population, people tend to remember or forget a similar set of images.
I think that's a hypothesis. My hypothesis is you're measuring popularity. So I'd like to see some tests that shows, yes, this is memorability, it's not popularity.
I mean, so we do have some tests which I'll get into later. So there's some correlation in some parts, but it does not, it's far from explaining memorability, yeah. Any more questions? So essentially, the point is that what we find is, to a large extent, memorability is a property of the image rather than the individual, at least on average. And to study this in more detail, we collected this large-scale image memorability data set consisting of 60,000 images and 80 views on each image. So let's take a look at some of the images that we found. So for example, this image is something that you might have taken going on a hike. You see a beautiful sun, and you're essentially, you take this image and you think, hey, I'm going to remember this forever. Turns out it's one of the most forgettable images in the data set. Now, for example, this image. You look at this image, you're like, why am I taking this? It's very mundane, and what does this even show? Turns out one of the most memorable images in our data set. So, interestingly, what we find is that people are actually really bad judges of what they will remember. So essentially, people behave like random number generators when trying to predict which images they'll remember or forget. So we essentially, like previously we did the experiment where we showed people these images and we measured which ones they remembered through the clicks. But instead, if you actually ask people, hey, do you think you're going to remember this tomorrow? And we'd actually tried phrasing the question in many, many different ways. We found that the best we could do is get people to have a correlation of 0. Otherwise, they're typically pretty negative. Yep. Or somewhat negative.
How the experiment we did so far answers the question of what picture will be rememberable tomorrow or 3 months down the line. Since the experiment is you have this stream of things you're going to go through in 5 minutes.
Mm-hmm.
More of short-term memory than long-term.
So technically, it's not short-term memory. So short-term memory falls under when the repeat is shown within about 20 seconds. Long-term memory is beyond that. And the repeats here are shown from 35 to 100 seconds. So it's definitely not short-term memory. Plus,
have you tried?
Yes. So there have, I have personally not done that experiment, but there was, the previous experiment had shown that if you also increase the amount of time between when repeats are shown, the decay is, there's a log linear decay. So essentially, the images that were memorable, which were shown after, say, a repeat of 100, were still the ones that were memorable after a delay of 100. Were still the ones that were memorable after a delay of 1,000. And they tested this for 100, I think 500, 1,000, and maybe a little bit longer. The nice thing is that the rank correlation between all these timings remains pretty high. So yeah, it decays it decays as you might expect with time and remains preserved over time. Yep. So some of the other things that we observed were, images with abnormal objects are very memorable. This is something that you might have expected. Certain weird images such as, the one with the chair made of straw or like a car flying tend to be extremely memorable. But again, it does not explain the entire part of the signal. So there are abnormal objects that are that have a memorability of 0.4, as well as there are abnormal objects that have a memorability above 0.9. So essentially, there's a whole range of memorability scores even for abnormal objects. All that we saw is that the mean is definitely higher than it is for regular images. Another thing that we observed is that the most memorable images, so the top 25% most memorable images, are more popular on social networks as well. But the remaining 75% have little to no correlation with popularity. Another thing that we saw is memorability is quite distinct from aesthetics. So you might expect that images that are really ugly or weird would tend to be extremely memorable because they might be outliers or something. But what we found through testing with other data sets that had aestheticness ratings is that memorability and aesthetics had a correlation of about 0. Yep. So we just tested aesthetics. Like there's an AVA data set, aesthetic visual, I forget the name. But essentially, that data set has ratings from people, from generic users for each image. So I think it had, on average, like 50 to 80 ratings from people saying how aesthetically pleasing that image is. And then we found we used that as part of our large-scale image memorability data set, and we found the correlation between memorability and aesthetics, and that was about 0. Does that explain? Yeah, cool.
Question?
Yep.
Does this correlate with like distance to nearest neighbor in some semantic space? Like, so back to Oren's point from earlier, if you look at a random distribution of Flickr images, you'll get a lot of landscapes. So it seems reasonable to me that landscapes are more forgettable. You'll see a bunch of them, and so any particular landscape won't stand out as memorable. But you'll see fewer images of people with faces with like ripped paper on top of them.
Sure, but no, I mean, so the thing is there's a lot of images with people, as you know, we essentially tried to balance the distribution. So there's some images that have, like it's, I would say, you know, less than 10% of the data set is landscapes, like just on average. And you know, a lot of images will have people of different sizes, people doing differently weird things. And there's some images that are just really hard to explain, that, you know, there's just a woman standing in front of a painting and there's nothing weird about it, but turns out to be extremely memorable. And there's many other women standing in front of paintings, but they're not as memorable, and it's not clear why. Yeah.
If you showed me a picture of, say, the Eiffel Tower or the World Trade Center, I'll probably remember the object. I'm not remember the exact image.
Sure.
So do you count that as memorable? Or?
So we actually, like, you know, so I didn't go into the specific details. We tried to discount familiarity. So, you know, we cannot completely get rid of that effect, obviously, but we try and minus out the false alarm. So for example, you know, I'm showing you an image first time and I'm showing you an image the second time, right? So if you press a key on the first time, that means that you're kind of familiar, you think you've seen this image before, but you actually have not. We actually subtract that from our analysis. So we try to deal with it. Does not solve exactly the problem you're saying, but this is the best solution we have thus far. Yeah. So you know, we saw that people were really bad at predicting how memorable images are. So can we build algorithms capable of predicting this, right? So what we do is we set this up in a very standard machine learning framework. We're given a set of training images, such as these ones, with associated memorability scores, as shown in the numbers there. And our goal is to build this function f that, when given a test image, you know, predicts how memorable it is. Right? So it's extremely straightforward. So what we do is we use the best known algorithm in the area, which is convolutional neural nets, which I'm sure many of you are very familiar with. So convolutional neural nets have this layer-wise architecture where they take, you know, given an image, they process it in a bunch of layers, and finally produce the output that you desire. The really cool part about ConvNets is that you only have to specify what you want at the output, and it learns what the representation should be in and of itself, without us providing supervision on, say, hey, use, you know, histogram of gradients, or you know, other types of specific hand-engineered features. So now that we have this, let's see how well it performs. So firstly, what we found is that the, you know, interhuman correlation was at about 0.68. So yeah. So the loss is like a Euclidean loss.
Is this a regression loss?
It's a regression Euclid, yeah, L2 loss on the output memorability. And the network was pre-trained with scenes and objects. So combining ImageNet and places, yep. And then fine-tuned, yeah. So, you know, the interhuman correlation, when we conducted the initial experiment of the visual memory game, we found that to be about 0.68. So, you know, essentially, if we did the experiment one time and we repeated the experiment again with a random new set of people, the correlation between the memorability scores that we found was at about 0.7. So that's kind of where you might expect the upper bound of prediction. Then, if we take a look at the previous state-of-the-art features, the prediction was at about 0.47. So this is using hog features. And this is actually not bad, given that, you know, humans have a rank correlation of about 0, you know, at being able to predict this. So we have something that works reasonably well. But when we applied convolutional neural nets, or MemNet specifically, we obtained a rank correlation of about 0.64. So achieving really close, you know, near human performance near human level performance on this task. So we can do a really good job at predicting memorability using ConvNets. So now it's great. We have this black box that's capable of doing this prediction, but what's going on inside it, right? Like, can we actually understand, or at least try and get at what this amazing black box that's able to do this prediction is doing inside? So can we, so we develop a process for visualizing neurons in deep nets. So the way is extremely simple. We essentially feed the neural net with a whole bunch of images. So for example, you can feed it 200,000 images, and you record the activations at different parts of the network. And once you've recorded the activations, now you can take an image that maximally activated some particular neuron. So let's say there's a neuron in Conv4 that this image activated to a large extent. So now how do we know exactly which part of the image is causing the activation? Right? So what we do is we take a simple patch like this one, a noise patch, and we translate it across the image. And based on this translation, we see how the activation is affected for that given neuron. So you can imagine putting this patch at different locations, and when it happens to cover something that's extremely important for it to have this high activation, the activation is going to go down, right? And based on that, we can tell what parts of images are important. And I'm not going into the details of this, but essentially what this allows us to do is find the receptive fields of different neurons across different layers and project that back to images so that we can see what are the discriminative parts of images. So what do we find, right? So this is our ConvNet. In the early layer, we just use it as the same size as the first layer filter, so 11 by 11 for AlexNet at least, and different ones will have different. But we found it doesn't really matter too much. It's just it increases the amount of computation, right? Because if you have a smaller one, it will have more patches that you slide. So what we found is that the early layers learn very simple things such as simple edges as well as colors. So just to explain this visualization, each of these rows shows images corresponding to a single neuron. And the parts that are in color are the ones where the neurons are activated highly. The ones that are blackened out are the ones where there was little to no activation for the neuron. Okay? So what this shows is the first neuron seems to be firing on this white-black edges, independent of orientation almost. The second neuron seems to be firing on this yellowish orangish color. Right? So these are the type of neurons that we tend to find in the early layers. If you go to the next layer, you see that the network starts composing information from the early layers of simple edges and colors into more complex edges, such as this one, which have both some dependence on color as well as a strong edge, and long edges, as well as textures or repeated patterns. And if you go even further into the network, you see that the network starts composing these textures and complex edges into shapes and object parts. So for example, the first neuron at the top corresponds to the circular shape, completely independent of what object category it's coming from. So there's a neuron that just fires on circles. And then there's a neuron for object parts. So this one seems to be firing on the windows of a building. And it's very specific to this object. And if you go even further, you find neurons that start specializing to objects and scenes. So essentially the first neuron seems to be firing on beds, and the second neuron is firing on scenes, such as the baseball field. And it's really remarkable that the network is able to do this because it was provided little to no information about where any of these things are, or that any of these things are actually important. Right? Because all you do is you say, I have an image which contains, let's say, a bed. The output should be bed. Why, the unit is actually able, the network is actually able to build units that specifically localize this bed automatically without having any, supervision like this. Yep.
Is this after learning on your own data set, or this is just?
I mean, there's some common neurons, right? Like after you fine tune. So I'll show. So these ones were more common ones. I'll show the ones that were specific to memorability right after this. So in general, this is really cool because it seems to be doing the past many years of computer vision research in and of itself. Because there are many people who are working on the low-level stuff, such as let's find edges and textures, and it's doing that in some of the layers. Some people were saying, hey, let's use object parts to compose objects or to find objects, and it's already doing that in and of itself. So essentially, it's a really powerful mechanism that we have here to predict memorability as well as a whole host of other things. So now let's take a look at some neurons that were more specifically correlated with memorability. So we took the activations of each of the neurons and found the correlation with memorability for each of them. So this was the one most strongly correlated, which seems to correspond to exposed body parts. So essentially, naked people are memorable. So that's nice, which is something that you might have expected. Secondly, faces tend to be memorable. Again, something that you might have expected. But it's nice that the network is learning to figure this out in and of itself. Another neuron that we find is this one. So it may look a little weird. It seems to be corresponding to circular shapes. But to me, it's one of the most interesting neurons. Because things that we cannot interpret but have a strong correlation seem to suggest that there's something that we don't know. Essentially, there might be something that we can learn about ourselves or our memory from neurons such as this one that tell us that maybe these circular shapes are very memorable. And that is why the spatulas that we had, that image of spatulas turned out to be extremely memorable. So now let's take a look at some of the neurons that are negatively correlated with memorability. Oopsies. Come on. Yes. So the first one, this corresponds to horizons. So essentially, these outdoor scenes and horizons tend to be quite forgettable. This other one corresponds to the tops of. Go for it.
The comment that you made about the last line, strong positive. So are you assuming that the way the neural network classifies memorable, non-memorable, is it humans do the exact same way?
I mean, it reveals something about how humans are doing it. So it may not be that the mechanism is exactly having these type of neurons laid out in a feed-forward path, but it might tell us that, hey, these are the type of patterns that are actually important, and we should investigate why circles tend to be extremely memorable. You see? So it's not like I'm not saying that our brain is wired in like a ConvNet way, right? That'd be weird.
That would be a pretty controversial comment about.
No, it's clearly not, right? But it may tell us about patterns that are important. So that's kind of, yeah.
I'm surprised you say that because I don't think anyone would remember the faces they saw in the initial set of pictures that you showed us. But we'll still be able to say, if you showed us the picture again, we'll still be able to say, yeah, we saw the picture before. But I don't think I remember anyone's faces there.
So essentially what this means is images that tend to contain faces tend to be quite memorable. So in this specific network, it doesn't get to the memorability of individual faces, and that's a different project that I have also been working on. But at least what it says is, the images that do contain faces are going to be more memorable than the ones that don't. Yeah. Yep. So now we have this cool tool that's able to predict memorability given an image like this. But can we actually tell what parts of images do people remember? So can we go in and make predictions of, oh, maybe, I don't know, the painting is memorable, but not the girl, or the other way around, right? So there's a very simple way of doing this. Now that we have this cool, we have this tool that's able to predict memorability, we essentially just apply it on a patch-by-patch way, right? Like we take one patch of the image, we use MemNet, and we get a score. And we can keep doing that for various patches. And this gives us some sort of heat map that we can represent like this, where red corresponds to the memorable parts and blue corresponds to the forgettable parts, or low memorability parts. Okay? And overlaying that on top of the image, we see that it seems that the girl is extremely memorable, but not so much the painting in the background. So taking a look at a few more examples, an image such as this one, what's memorable are the people as well as the chandelier, but not so much the utensils in the kitchen and what's going on in the background, as well as what's on the table. If you take a look at the image here, it seems the zebras are very memorable, but not so much the dirt road that they're standing on. Here, the text seems to be extremely memorable, but not really the leaves in the background. So this is all well and good, and you can kind of do this with any machine learning algorithm, but it's a little unsatisfying, right?
You tried validating this hypothesis?
I'm glad you asked that. Okay, so yes, I was waiting. I was just like trying to prime that question. Thank you. So yes, it's not satisfying given that you can do this with any old machine learning algorithm. So how do we go about validating this thing, right? How do we tell if people actually remember the text or the leaves in the background, right? So let's take a look at one example image such as this one. Now, given a map like this, what we do is we modify the image to enhance the details in the parts that the algorithm predicts are memorable and reduce the details in the parts the algorithm predicts are forgettable. So for example, we create an image like this one. So you can't really see the cars in the background here, but you can tell that there's a giraffe here, right? As well as all this part of the image is gone. And on the flip side, what we do is we modify the image to remove the details from the memorable parts and enhance the details in the forgettable parts. And then we put this back on Mechanical Turk and evaluate the memorability, like compute the memorability for each of these images. So fortunately, what we find is that the ones where the image was modified to enhance the low memorability regions had a lower memorability score than the opposite image. And here's a few more examples. So as control, what we did is we included an image where we randomly, we assume that there's no heat map, and we randomly enhance the detail of different parts of the image, and reduce the detail at other parts, such that on average, the amount of detail for high, medium, and low is the same, while where high is using the heat map to enhance the high memorability, low is using the heat map to enhance the low memorability. Yeah.
Why focus on changing the detail? Why not just block out the parts that are low?
Because it might introduce other weird types of biases. So for example, it says person is memorable. I carve out the shape of a person. You might still think, in your head, there might still be a person there. So we kind of we want to try and make it a little bit more smoother transition between the two. Yep.
Psychologists have been doing these studies for decades where they have a device that tracks your eyes as you look at a picture.
Mm-hmm.
And they draw on top of the picture where your eye is going.
Sure.
And they find that people look at faces and bodies and ignore backgrounds. It'd be interesting to see the correlation between your heat maps and these traditional things that psychologists do.
Great question. So that's about 0.2. So essentially, I think what people fixate on, the things that people remember, I think, are a subset of the things that people fixate on. So you might look at different parts in the image, but you won't remember all of them. That's what we have found. So what we did was, we collected our data set. So in our data set, we included a lot of popular saliency data sets so that we were able to evaluate this thing well. Yeah.
So
Yep.
after you do some form of painting, so those are not natural images anymore, right? So meaning that people are not actually comfortable looking at them.
It was, so what we, to ensure that everything is not, like we just did everything not natural. So, even like including the fillers that were not repeated, as well as, like essentially all images had this weird effect. So within that, we still found that people had consistency in what they remembered. And when we conducted these 3 experiments, the memorability of high on average was significantly higher than medium, and low was below that. So we did this for about 1,000 images. And it was pretty consistent. So essentially, our algorithm is able to do a good job at predicting which regions of images people tend to remember. And we could validate that. Yeah.
Have you thought of using this region memorability predictor to do image captioning?
That is a great question, and that's something that I potentially might look at in the future. So essentially, the way I have been thinking about that is, can we make captions that will make people remember images rather than just focusing on random things in the image to be able to caption it? So essentially, it's a measure, like it's a notion of, I mean, I don't know if people have looked at it with saliency and such, but you can think of it in a similar light, right? Like you want to focus your attention on things that will allow people to recall this particular image. So it's a more useful type of caption. Yeah. But I've not done any work on that yet. Yeah, so using this technology, we developed a demo that we put online where people could put in a URL, like upload their images and start seeing the memorability scores of those. This was picked up by a bunch of popular media outlets. And it was great to see like the real world impact of this work. We had more than about 2 million images uploaded in, I think, about a week or a week and a half. And it was great to get emails such as this one from people who were extremely passionate about how the system was scoring the images that they deeply cared about. So essentially, if you take a look at these images, they're just they're pictures of girls' faces, right? And faces is something that we all care about deeply, right? Like faces is all around us, and it defines people. And I don't know if you've had this particular experience where you have been at a party, you meet someone, you say hi, and then you go around the room talking to other people, and then when you come back and talk to them, they don't remember you at all. They have no recollection of having met you in the past. And maybe the problem is that your face is extremely forgettable. And fortunately, we have a solution for that. So given a face such as this one, we can modify it to be more memorable here. So let me show you again. Without changing the identity, or at least to a large extent, without changing the identity of the individual, we can modify a face to be more memorable. So for example, an image here, we modify it to be more memorable. Image here, modified to be more memorable. So this is something that we have tested rigorously, and to a large extent, our algorithm can actually make meaningful changes to faces to make them more or less memorable. So how do we go about doing this, right? So it's extremely straightforward. We use this like active appearance models. So essentially, we have a face which has a set of landmarks as the red points shown here, and based on these landmarks, we can start tweaking the face. So essentially, we have a parameterization of a face, and using these landmarks, we can like move it around. So for example, we add a little vector x prime, and it becomes slightly different, or we subtract that same vector, and it becomes again slightly different again. Okay? So this means that we can start moving around in face space. So now what we do is we define a cost function that allows us to make predictable changes to each face. So we have a cost function such as this one, and we have 3 terms. So the first term is the cost of modifying identity, right? So ideally, the algorithm shouldn't just take your face and replace it with, I don't know, Julia Roberts. That will definitely make it extremely memorable, right? But that's not the goal here. So we want to preserve identity. The next thing that we want to preserve is attributes. So for example, if a face started out being a guy or a dude, it shouldn't be modified to start looking like a woman, right? Or he may not be too happy about that. Or alternatively, if he started out looking 30, he shouldn't start looking 65 by the time you're done, or 15, right? So there's a cost to modifying the attributes associated with the person, or associated with the face. And so now we see that both of these terms actually cause the face to remain exactly the same. because if we change the face, we're going to pay a price on both of these terms. So we need to have a contrasting term, which is the term for memorability, right? And this causes, so this says, hey, you pay a price if you don't make the face 10% more memorable than it currently is. And using this cost function, what we can do is we randomly sample faces close to our original parameterization or close to our initialization and iteratively update it based on this cost function as the cost function gets minimized. So it's an extremely simple approach. You start at this initial point, you sample a bunch of points close to it, you evaluate the cost function, and that's your next step. And you do that iteratively until you have optimized, or you do that for a fixed number of iterations. So again, this work was again covered by a bunch of people in the press, and someday we hope that we're able to build an app where people are able to change the memorability of their face in the palm of their hand. And looking forward, I hope we can extend this approach to start modifying memorability of images in general. So for example, an image such as this one, using the heat map, we realize that, oh, this part doesn't tend to be very memorable. Can we now use a large database of images and potentially fill it in with something else that might make the overall image more memorable, right? So this is something I have not done yet, but I hope would be interesting, in the future to be able to change memorability of images in general. So, a natural question that often comes up when I start talking about being able to change how memorable images are is, what if you made all images extremely memorable? What's going to happen? Are people just suddenly going to start forgetting everything, or remembering the same amount, or would we be able to actually increase how much people remember, right? And to do to evaluate that, we did a simple test. So we built 2 different settings of our visual memory game. In the first one, we randomly sampled images from our data set. In the second one, we took the 1,000 most memorable images and only tested on those. So we tested each of these 2 settings independently. For the first one, we found that of all the images, people tended to remember about 72% of them. So this is something that's extremely repeatable. You can try testing the memory of MTurk workers. On average, they tend to remember about 70 to 75% of what you show them. But very surprisingly, when we showed them the most memorable images, they were suddenly able to remember 93% of them. And this is statistically the same group of people. And this is an extremely powerful result, because it means that potentially by showing people more memorable content, we might be able to increase the amount that they remember. And this is something that I'm in the process of testing with this company called Edmodo, which has access to a whole lot of students. So essentially, I think this concept can be really powerful for learning, where people are trying to learn about, I don't know, geography, history, science, and so on. And in many of these things, you have diagrams, you have images that kids, that students want to remember. And we're in the process of applying this concept of memorability to images by showing certain kids more memorable, certain kids less memorable images, and seeing if it has a measurable impact on test grades. So taking the, kind of connecting the dots between memorability and understanding, right? Because just because you remember it doesn't mean you actually have a good sense of it. And we want to try and connect the dots to see if this could be much more useful and applicable for making kind of the textbooks of tomorrow. You had a question.
My question was, I think, to answer what you said. But you're kind of connecting the dots, right? Requires seeing whether if something's more memorable, it's also more understandable, recallable. It may or may not be the case.
Exactly. And that's exactly why we have, I'm using this platform to test this thing, because they have students, they have access to about 60 million students, and we can show them different types of content and then see if it has an impact on test grades a few months later. And if we can show something, that I think that would be extremely powerful. So Another area that I've been looking at is, does memorability apply to other modalities apart from just images? So, is there something like music memorability? So are there certain snippets of songs that are just extremely memorable while others are very forgettable? And our initial results suggest that it does exist, to some extent. So we do find correlation between what kind of short music clips people remember. And maybe that might help us explain why certain genres are more popular than others. And it might just be because they stick much more easily in people's minds. But this is something that, we're in the process of exploring further. So, that kind of concludes the part on memory. And now moving on to private traits. So can we predict, okay, to motivate that, let me just show you a quick video.
It was like this crazy-eyed, hairy beast man. It was like a Bigfoot or a Yeti or something. Hi, just so you know, we didn't mean to fog you. We actually thought you were like a Yeti or something. Hi.
So you like the short hair better?
What? Yeti? Danny?
So essentially what this clip showed is that people are using physical appearance to make judgments about each other all the time. In fact, there has been some recent work from Stanford that has shown that Facebook likes are able to predict your personality to a large extent, almost to the extent of your spouse. So what this graph here shows is what happens. So there's a graph from a paper from PNAS from Stanford last year. So what this shows is as you increase the number of likes that you look at for someone on Facebook, so likes correspond to things like, you like TV shows, you like certain celebrity figures, you like, other pages and such. But it does not correspond to the likes that you routinely click on your newsfeed. So it's more on the, big picture likes of people. And for example, like certain pop stars and so on. So what you can do is you can use these likes to then predict someone's personality. So in this case, what they had done is they have a bunch of people who had taken this personality questionnaire consisting of about 330 questions, which allowed them to break down each person's personality into these 5 factors of openness, agreeableness, extroversion, conscientiousness, and neuroticism. So what they do is then they ask different people to predict these factors about you. So for example, they could ask your spouse, they ask your family, your friends, and your work colleagues. So your spouse is the one who does the best, as one might expect, with a correlation of about 0.6. Next best is your family at about 0.5. After that are your friends at 4.5, and the worst are work colleagues at about 0.27. And if you look at the average accuracy of a computer trying to predict the same thing, it's at about 0.56. So there's a lot of information. You can tell a lot about a person just based on the set of things they like on Facebook. And then we had, I had another question. So this gives you a lot of structured information, right? Like it tells you, certain TV shows are liked by people of certain personality, as well as certain public figures, certain groups, and so on. But instead, can we now use someone's face to predict their personality? So just a single image of someone's face, using just a single image of someone's face, can we tell who they are? Right? So this work, I'm working with Michal Kosinski, the author of the previous paper on this. And what we have found is that our systems are actually capable of predicting personality almost to the same extent as a coworker. So given just a single image of a face, you can actually tell almost to the extent of someone who has met you, interacted with you, works with you, what someone's personality is. So it's at about 0.25 correlation. And here's some examples of images maximized for each of these different traits. So for example, extrovert versus introvert, we find some basic facial features such as, I think extroverts tend to wear makeup more frequently. You can see some glasses on the introvert. And you can see like the facial structure is extremely different between the extrovert and the introvert. And this is after accounting for a whole lot of biases that we could think of, such as, so this is just for females. Then we accounted for race. So this is just for like white females. Then we accounted for age. So this for, we normalize the prediction by, normalize the signal by age, because certain attributes, like certain personality attributes, change predictably as you age. And slowly we have been trying to normalize for every different kind of thing that we can think of to see if there's information in just your facial structure about your personality. And the question that I hope to look at in the future is what comes first, your personality or your face, right? So if you have a face of a certain kind, does that mean you're going to grow into some kind of personality, or the other way around, right? And I think that's something that would be extremely fun and interesting to explore. So why does it matter, right? Like as machines,
On the previous experiments and the Stanford one, how do you get the ground truth?
So this was a questionnaire that people had taken. So these individuals themselves took a questionnaire.
So what they think of themselves?
Yeah, so this is a well-accepted, I guess, sufficiently well-accepted personality questionnaire. It has 330 questions. And I mean, to me, of course, that again can be questioned. But to me, the thing that is that suggests that there's some information is actually the correlation of the different types of people who you expect would know you better, do know you better based on this. So yeah, that's kind of my assessment of, and my collaborator assures me it's a good thing to do. Anyways, essentially as machines become more pervasive in our environments, and they start to interact with people just like humans do, it's important that they understand people, right? And this is one of the ways that we can start understanding people using just visual data. And people also adjust the way they interact with people based on each other's personality. And it would be great if machines could become part of this process and become integrated by understanding who people are. The thing that to me is extremely exciting and much more important, well, not necessarily much more, but also very important, is human-human interaction. So can we make the process of human-human interaction smoother, easier, by understanding people in this way? So we are constantly forming new relationships. So for example, you're picking who your friends are, you're picking who you're dating, you're picking who your spouse is. You're essentially interacting with a whole lot of different people all the time. And if we can make the process of selection or matching so much easier by using visual information, where instead of having to go through, instead of having to date 100 people, we find you the top 10, won't that make the process significantly easier and hopefully save people a whole lot of headache? Right. So now, then moving on to, can we predict someone's state of mind? Again, to motivate this part, let me show you a short video clip.
Look him in the eye. I know I can get him to forgive us. I don't know. I'm telling you. I can do it. Yeah, you can do it.
So, while I have not gotten all the way to predicting someone's state of mind yet, as this video shows, your gaze, or where you're looking, reveals a lot about your state of mind. As we saw, Joey used his eyes to convince Ross that he can do it. And a lot of my work recently has focused on trying to predict someone's gaze. So I've looked at gaze from two perspectives. The first, from a third-person perspective. So we call this gaze following, where you're given as input an image such as this one, and your goal is to predict where each of the individuals in the image are looking. Okay? So the ground truth is shown in red, which is annotated by people, and the prediction of our algorithm is shown in yellow. So it's actually able to start doing a reasonable job at predicting where people are looking. Here's another example. So people like looking at pizza. and food, and basically there's so the algorithm is actually able to do pretty well. It's not yet at the human level performance, but it's actually able to do a pretty good job at predicting where people are looking. The other perspective that I've looked at this problem at is from the perspective of the device. So can we tell where people are looking at the device? So this is something so this is called eye tracking, and I'm sure many of you are familiar with this. This is something that has been around for a long, long time. It's nothing new. I didn't invent eye tracking. And it's something that's extremely useful. It's been around since the late 1800s. People have used it for something like medical diagnosis. So by showing people certain stimuli and recording how their eyes respond to those stimuli, you can actually tell if they have certain mental disorders or early onset of certain mental diseases. Another thing it's useful for is for building user interfaces, right? People have been talking about this for a while, but it has never been integrated into our modern user interface. Another thing is understanding people in the wild, right? Wouldn't it be great if when people are using apps or other types of devices, you could keep track of where they're looking constantly? And last but not least is it's very powerful as a scientific tool, right? All of us in vision have been using it for saliency, and it's actually used in many, many, many different areas, including psychology, medicine, and plenty of others. So the question is, why don't all of us have an eye tracker? This is something that's extremely useful, and as we have seen here, and all of us have mobile phones which have cameras. Why can't they track eyes, right? So let's take a look at the current state of the art. So there has been some progress. So this is the best eye tracker we have in the lab. So this is something that's extremely accurate, obviously very comfortable, and costs something like $30,000. It's surprising not all of us already have one of these. And if you look at the more recent developments, there have been devices that have been produced that allow people to track eyes, and they've become affordable. They're a few $100s, but yet eye tracking is not a pervasive technology, right? Because sorry.
It's in the Samsung Galaxy 5.
Not real eye. It just follows your eyes when you look down. It's like a blink detector. It does not act you cannot actually click icons using it.
It blinks the screen if you look away from it.
But that's not eye tracking. That's just sure, it's like a very primitive form of eye tracking. So I'll show you what the state of the art is, and that's probably what they're using. So essentially, these type of devices have prevented eye tracking from becoming a pervasive technology because there's no reason to buy the device because no applications exist for it, and there's no reason to develop applications because hardly anyone has the device, right? So the next obvious solution is to use your mobile phone, right? But turns out eye tracking on the mobile phone is pretty hard. So imagine that you're looking at this dot in the center. If you take a look at state of the art, this is what it tells you. Within this circle, it can tell you that you're looking there. So it can kind of maybe sort of tell you that you're looking at a phone. And that's probably what you're describing. And people have used it to maybe look down and it scrolls the thing for you. Not very promising. So we realized that one of the biggest issues with this is the lack of a large-scale data set. So to tackle that, we built this extremely large-scale data set. You can see people here. Containing more than, so currently it actually contains about 1,500 people with 2.5 million frames. And this, so we use crowdsourcing to scale this up to be more than 30 times the largest data set that exists yet. And there's a paper at CVPR. Using this, combining this with ConvNets, we're actually able to build a system that can tell within 1.5 centimeters without calibration. So without someone actually going in and looking at certain points where they're looking. So within an accuracy of about 1.5 centimeters. And this can be reduced to about 1 centimeter with calibration. And plus, it runs on mobile devices at 10 to 15 frames per second. So we use certain methods to optimize the deep net such that it can run really fast on modern mobile devices. So with this, we hope that we're able to bring the power of eye tracking to everyone. And now, combining these things, this is a system which is potentially possible of predicting state of mind, but I will not go over this since I'm running out of time. So in summary, I talked about how we can predict human memory, private traits, as well as someone's state of mind. And with that, I'd like to end my talk. I'd like to thank all of you guys for listening, as well as all of these wonderful people who are my collaborators, without which none of this would be possible. All right, thank you.